When working with catalysts, chemical engineers need to be able to define concentration profiles to model the systems that they work with. So if we are using spherical catalyst pellets, for example, that are porous, being able to figure out what the concentration is as a function of the radius inside the pellet, so we can have an idea of what kind of rate of reaction we can expect to have, is a very important topic to understand in an engineering context. And so what this video will cover is something referred to as the Thiele modulus and the effectiveness factor. And these are terms used to help us figure out what these concentration profiles will look like inside pellets as functions of the radius of the pellet. And heads up, there are different types of pellets. Spherical pellets is what this derivation will discuss, but we also have slabs, just big blocks or slabs, as well as cylinders. And so those have slightly varied derivations, but the gist of the math is the same, but you will end up with a different final model. And so, to begin with, what we do is, let's say we had a spherical pellet that's porous, and what we're going to perform is something referred to as a shell balance. And we're going to do a mole balance on this differential annular region between two spheres, and that will be our control volume, from which we will ultimately derive a Thiele modulus, so that we can get a rate of reaction from the effectiveness factor that comes from our Thiele modulus. And so what we're going to do is we're going to analyze the control volume between R and R plus delta R. So essentially, it's essentially like it's a spherical annular region, a shell. Hopefully, I'm not being too redundant, but starting off with the mole balance, we have no accumulation because we're assuming we're operating at steady state. We have an inlet term, an outlet term, as well as a generation or consumption term of our species A. A is our reactant in this case, as it's moving through our catalyst pellet. And A is coming from the outside in. So we have a higher concentration of our reactant on the outside of the pellet, and A is being consumed as it diffuses through the pellet. And so the whole purpose of this is to figure out the balance between the rate of diffusion and the rate of reaction within the pellet, because inside the pellet, A can either diffuse farther in or it can react. And so this is why we need to know what the Thiele modulus is. And so what we are going to do is we're going to use flux of A, which is denoted WAR, so flux of A in the radial direction, evaluated at R plus delta R, the outermost shell, coming in to so this is our inlet term, and because flux is quantity per area per time, we need to multiply this by the area that we're working with. So our outermost shell will have an area of 4 pi times R plus delta R quantity squared. And then coming out of our control volume, we will have a flux of WAR valued at R, and then again times the area. And then within this annular region, we can have a reaction occurring. And so K sub n prime prime refers to is a reaction rate constant per area. So when you see prime prime, it's a common notation used by chemical engineers to mean that it is a rate per area. And then we are keeping things generic, so we're saying this is for an nth order reaction, so Ca to the nth power times a quantity referred to as A sub I, which tells us the surface area per volume of the pellet. This is an intrinsic property of the pellet, and commonly you'll be given this value either by the manufacturer or on a test. And then the next thing we need to do is multiply by the volume of the shell that we are working with. And because we will later take the limit as delta R goes to 0, what we can approximate this volume of our annular region as, we can approximate it as 4 pi r squared times delta R. So if we thought we had some kind of shoebox or something, the height of the shoebox would be delta R, and then the two top and bottom plates would have an area of 4 pi r squared. So this gives us our volume. And so when we plug in these quantities and we divide all of our terms by 4 pi delta R and take the limit as delta R goes to 0, we end up getting, by the definition of derivative, a value ddr of WAR, the flux of R in the radial direction, times R squared, minus, and then this is a simplified version of the rate of reaction that's occurring of A within our annular region. And the next step we're going to do here is we're going to want to rewrite this flux term in terms of concentration. So we're going to turn to Fick's law to do that. And Fick's law, if we have no convection, tells us that the flux of A in the radial direction is equal to some kind of transfer coefficient, in this case the diffusivity minus dAB, times the concentration gradient of A in the R direction, dCA dR. And again, just to make sure, this has units of mole of A per area per time. So we plug this quantity into our mole balance, and what we see is that this diffusivity term, or diffusion constant, we can pull out and then take the derivative. And because we have two functions of R, we need to do the product rule with this derivative. And so when we do that and we pull out the minus diffusion constant, we end up getting R squared d2Ca dr squared plus 2R dCa dr, and then minus the term we had before. And so to simplify this further, what we're going to do is divide all these terms, because we want to isolate d2Ca dr squared, by minus dAB times R squared. So this ends up getting us to this expression here, which is an important one to be able to arrive to on your own, because commonly you'll be asked to derive this on a test, and from this point on, what we can do is write concentration profile of A as a function of R if we integrated this expression. So this is an important equation to be able to arrive to, but for deriving the Thiele modulus, what we will instead do is non-dimensionalize it. But the point is we've arrived at this equation here, which is a pivot point, which is an important equation to get to. And the boundary conditions we would use if we wanted to actually get a concentration profile of A in the R direction would be, we would say Ca evaluated at R is equal to the CAS, the surface concentration of A on the outermost surface of the pellet. Big R represents the entire radius of the pellet. And then also, by symmetry, we can say that if you looked at a concentration profile of A as a function of R within the pellet, so this would be R, we would expect to see some kind of downward slope because it's reacting. So as we move inward, so this would be the center of the pellet. As A is diffusing in, it's being reacted. And the y-axis corresponds to the concentration of A. Sorry if this doesn't show up too well, but the point is that if we take the slope of Ca as a function of R, we expect to have a slope of 0 at the center by symmetry of this pellet. And so getting back to actually deriving the Thiele modulus, what we can do is non-dimensionalize this equation by defining two variables, non-dimensionless variables called psi, and we're going to call that Ca, and this is Ca evaluated at any R, divided by the surface concentration of A. So we've got molarity divided by molarity, has to be dimensionless. And then another variable called lambda as little r, whatever radius you are at within the pellet, divided by big R, the total radius of the pellet, and that has units of length over length, which is dimensionless. And so one method to go about this is to now define CA as psi times CAS and R as lambda times R. And we're going to plug this into the equation, which I call star. And when we do that, if we look at the first term, d2CA dr squared, and we look at how we can plug this or non-dimensionalize it, if we plug in the value CA for psi CAS and for little r as lambda times big R, because R and CAS are all constant values, they are not functions of the concentration or the radial direction we're at, we can pull these terms out. And so what we end up with is CAS divided by R squared, big R squared, times d2 psi d lambda squared is equal to d2CA dr squared. So in star, if we multiplied star by the reciprocal R squared over CAS, when we plug in our definitions, we will end up with an equation that has dimensions of nothing, which is what we want. And doing that, if we another important thing to note in this equation is this third term here. When we multiply this third term by R squared over CAS, if we call CA to the n equivalent to CA times CA to the n minus 1, we can extract psi from this expression and have CA to the n minus 1 power in our third term. And once we've done this, what we see is that we end up getting a mole balance that is now dimensionless, d2 psi d lambda squared plus 2 over lambda d psi d lambda plus, and then this term is the term that is your Thiele modulus squared, k prime prime, and this is for an nth order reaction, times AI, I'm sorry I didn't define this earlier, but AI refers to the surface area per volume of the pellet, times big R squared, the total radius of the pellet, times CA to the n minus 1 power, where n is your reaction order. And we divide this term by DAB, the diffusion constant, and then times psi is equal to 0. Just this quantity that's boxed in is your actual Thiele modulus, and it's a square of the Thiele modulus. And this is how you arrive at your Thiele modulus squared for an nth order reaction. So commonly in textbooks, you'll square root this, and you'll have an r to the first power out front times this stuff. It's also important to note that in this derivation, I assume that DAB was equal to D effective, but that's not always the case, and you can look it up on in your textbook as to the quantities that are involved to this really should say D effective, but then you can look that up. And then the next thing to note here is, so now that you have a Thiele modulus, what good does that get you? So there's another relationship we will define when we have strong mass transfer limitations. We define our effectiveness factor, eta, to be 2 divided by the reaction order plus 1 to the 1/2 power, 3 over phi sub n, the Thiele modulus of an nth order reaction. And the reason this is important is because we ultimately arrive at this relationship which tells us that the observed rate of reaction is equal to eta, your effectiveness factor, times R sub A evaluated at CAS for all R within the pellet. And so dissecting this a little bit more, what this means is that if we assumed that there was no internal transport limitations and that the pellet was isothermal, the ideal rate of reaction, if every spot inside the particle was at CAS, this is what would have happened. So if there were no internal transport limitations and the pellet was isothermal, eta would equal 1. But it's common that, and another important thing to note is eta, it's tempting to call eta some kind of efficiency value, but that's also not accurate because eta can be greater than 1. in the case of an exothermic reaction. So if somehow our reaction is generating heat, then there's an Arrhenius relationship between the rate constant and temperature, which is an exponential relationship. Because the pellet is not isothermal, the reaction is actually happening even faster as you diffuse in. So eta can take on any value between 0 and infinity, although it's pretty unlikely it'll equal infinity, but common values of eta usually from around 1, less than 1. It can be less than 1 to 0 or greater than 1 within reason. And so I hope you guys find this helpful, and let me know if you have any questions. Thanks.